of 2018. The Warren Lecture Series is made possible by a generous gift from Alice Warren Gardner, and we're very appreciative of that. Our speaker today is Dominik Schillinger. Dominik is assistant professor here in the Department of Civil, Environmental, and Geoengineering, where he teaches courses in structural mechanics and does research in simulation-based engineering sciences. Dominik obtained his bachelor's degree at the University of Stuttgart, a master's degree in structural engineering at the University of Connecticut, a master's degree in computational mechanics at the University of Stuttgart, and a PhD degree in computational mechanics at the Technical University of Munich. After completing his PhD degree, he went to the University of Texas at Austin to work with Tom Hughes at the Institute for Computational Engineering and Sciences. And he's been in the Department of Civil, Environmental, and Geoengineering here at the University of Minnesota since 2013. Dominik's research interests are in computational mechanics, focusing on the modeling and finite element analysis of multiphysics and multiscale mechanical systems. And applications of his research range from aerodynamic structures to biomedical imaging to simulation of resistance characteristics in agricultural products. Dominik's work has been very well received by the technical community, and he has been awarded some very prestigious awards, including the John Argyris Award from the International Association for Computational Mechanics, the Richard von Mises Award from the International Association of Applied Mathematics and Mechanics, the Zinkayevich Award from the Institution of Civil Engineers, and a Career Award from the National Science Foundation. So without any more ado, please give a nice round warm of applause to introduce Dominik.
Thank you very much, Art, for your kind introduction. I really appreciate having the opportunity today to talk a little bit about my research. And I want to take this opportunity to give you an overview of the spectrum of work in computational mechanics that is currently underway in my group. And to this end, I chose three rather different topics. One is on isogeometric trimmed shells, which covers research on innovative discretization technology. The second one is on imaging-driven microstructure upscaling, which covers physics-based modeling. And the third one is on variational multiscale modeling, which is rather, let's say, numerical analysis and applied mathematics oriented. So I want to start talking about shells. So shell structures are 3D structures that are characterized by the fact that one spatial dimension is significantly smaller than the other two. And this enables their modeling by a dimensional reduction such that their mechanics can be fully characterized by the deformation of a surface. And shells are ubiquitous where reducing weight and material is essential, such as in the automotive industry, aerospace, marine structures. And the evolution of these, what I would call high-performance, highly optimized thin structures today, a cornerstone for that is today's design process, which really relies on the the close interaction of computer-aided geometric design on the one hand and finite element simulation on the other hand. So today's design through analysis pipeline can be basically conceptually summarized as follows. So if we want to go from a new product idea to production, we first model the new component in a design environment based on computer-aided geometric design. And then we undergo usually several cycles of virtual testing by the finite element method. The characteristic problem here is that we can't directly go from design to analysis, but we first have to do this model preparation step, which consists of defeaturing, geometry pair, and meshing, to basically transfer the geometric model of CAD that is based on smooth splines to a finite element mesh that represents the geometry by C0 continuous Lagrange polynomials. And this leads to a poor interoperability of today's CAD and FEA, with a very large amount of time of this virtual testing cycle devoted to the transfer of the geometric model in the model preparation step that usually accounts for 70% of the time and up. To illustrate a little bit how significant that problem is, this is an email I received a couple of, 2 years back from MSC Software, which is a distributor of one of the major commercial finite element software tools, Nastran. And that was in preparation of a new release of their software, and they with a series of webinars, and one of those webinars was entitled "Cut Hours of Time Editing Geometry and Meshing." So we see that a major argument for selling commercial finite element code today is not so much the power of the actual finite element simulation engine, but the flexibility of the geometric preprocessor. So now we come to this new technology, isogeometric analysis. So what that major goal of that technology is to unify design and analysis by enabling a seamless CAD and FEA integration into one single software framework. And its basic idea is that finite elements can use the same smooth and higher order basis functions as they are used in CAD, such that you can seamlessly go back and forth between CAD and FEA representations. I think that this is particularly convincing. This concept is particularly convincing for shell analysis for several reasons. One is that CAD explicitly parameterizes the physical domain if you have a shell. Yeah, so the surface is directly the physical domain that you use in analysis. Yeah, this is not always the case. If you think in terms of 3D structures, they're often given in terms of boundary representations, where you have a surface parameterization, but not a volume parameterization. Then in the case of shell analysis, the CAD model and shell finite elements are based on the same surface operation based on differential geometry. And the third point is that the smooth basis functions are ideally suited for discretizing higher order differential operators as they arise in thin shell theory. There is, however, one significant bottleneck, and that is the trimming concept. And I would like to outline or illustrate what that trimming concept is by this little example. So here we see a design process of 3 intersecting tubes, yeah, as they, for example, could appear in tubular, as a connection in tubular truss structures. And what the designer wants to do is he would like to replace these sharp interfaces here by smooth surfaces. And he does not, so he uses the trimming concept. So the trimming concept does not change the original parameterization of these tubes, but in a first step, he adds so-called trimming curves. These are these guys here. So these are spatial curves that are defined in the physical space as well as in the parametric space of these surfaces, and they have topological properties associated with it, such that you basically can trim away parts of existing surfaces. Yeah, so that is this trimming procedure. At the same time, you can also add additional surfaces, and that's what he's doing now, that basically kind of try to fit as best to these trimming surfaces as possible, yeah, to any given tolerance. But the problem here is with trimming surfaces that are connected along trimming lines is that they're not fitted. Yeah? So you see here, this is the parameterization of this inner trimming surface. So you see that the lines along the parameter lines along these trimming lines lead to cut elements in the parametric domain. So from a visualization standpoint, everything is very smooth and looks very nice. But from a parameterization standpoint, we have several challenges. One is we have to deal with cut elements. And the second challenge is we have to make sure that our physics here, the shell physics, are correctly transferred between surfaces across unfitted trimming curves. And here is our take on how we can deal with these challenges. So the first one is we would like to integrate accurately trimmed elements. So in finite elements, we typically evaluate these integrals by quadrature. So we need some quadrature rule that can evaluate this integral by evaluating your function to be integrated at certain quadrature point times corresponding weights. So the task is to find these locations and the corresponding weights that can give you an accurate integration over a cut surface in the physical space. So what we know is we know the parameter space of the spline surface. And the interesting thing there is, of course, how to deal with the cut elements. Yeah? So here we have one of those cut elements. So what we can get from CAD data structure is any cut spline element together with this trimming curve in the parametric domain of the spline. Now, we know that Gauss quadrature is defined in uncut elements. So what we do in order to integrate this accurately is we define new so-called quadrature elements that we can map forward to the cut spline element in such a way that we can parameterize this accurately. A problem is, of course, that topologically your cut might not fit to this quadrilateral here. So what in this case we do, so here we have a pentagon, for example, that cannot be mapped from a quadrilateral. So what we do in this case is we just cut the cut parametric element until we have subcells that we can directly obtain from quadrature elements. And then we have a series of mappings. Yeah, so here we know locations and quadrature points. And then we have a series of mappings that give us accurate locations and accurate weights in the physical space to do integration accurately over cut elements. So the second challenge is the coupling along trimming curves in a physically, let's say, consistent way. So here our idea is to transfer technology from discontinuous Galerkin methods to trimmed shells. So the idea in discontinuous Galerkin methods is that you formulate the physics on one element, on each element individually without considering other elements. So that would be some physical equation, then you transfer it into a variational form by integration by parts, and you get these surface flux terms on each element along element interfaces. And then you use basically opposing flux terms, and you replace them by numerical fluxes that basically define relations between physical quantities on both element interfaces such that they connect in let's say, physically consistent way. And then you can go a little bit forward and transform this, and you get one variational form that contains the usual weak form part, plus integration over element interfaces that make sure that these elements are connected. So now we transfer this to the trimming part. So here we have a similar situation where we have patches of spline elements that are trimmed by these trimming curves. And we can now identify basically these trimming curves as analogies to these element interfaces and do go through this exact same mathematical procedure to deform these interface terms that guarantees that they're coupled correctly. Yeah, and they, of course, in the shell case, it's a little bit more difficult expression. So here we get something over this integration over these trimming curves here that gives us something that couples the forces together. So this is basically the average of forces times the displacement jumps. And the second row basically couples moments together. So here we have the average of the moments times the jumps or possible jumps in rotation. And these terms here are for stabilization. OK, now the question is, how does that work? And to illustrate this, I would like to present a benchmark study that I recently carried out together with a startup company, Faircat 3D, that operates out of Santa Fe, New Mexico. And this company has direct access to real-world shell designs, for example, as they're used in the design of this car. Yeah. So here we're focusing on the car hood. So this is a real CAD model, as it is used in industry. And we define some arbitrary boundary conditions, so we fix it here and here for testing purposes, and we apply some load in this fashion. And then with our method, we are directly able to do analysis. There's no meshing, no geometry cleanup. We use our trimmed shell analysis directly operating on these spline elements. These are the spline patches, basically, the individual surfaces. These are the underlying surface elements. And we are leveraging the trim data structure in terms of trimming curves and topological relations to correctly deal with connecting trimming lines and integrating over cut elements. If you compare this to the standard way to do this right now, you can look at in a standard finite element code. This here is Abacus, and here you would have to get a mesh, a separate geometry representation than this one. So you have to transfer this geometry representation into this mesh. For that, you have to use, first of all, geometry repair. So you load this geometry into Abacus. It gives you this picture where each red dot basically signifies one geometric problem that needs to be cleaned. And for this relatively simple geometry, Abacus can do that correctly. but FairCAD 3D could always add additional operations, like changing the surface a little bit, arriving at geometry problems that Abaqus couldn't handle. Yeah, one example, for example, are these very small, tiny trimming segments. So if they add tiny trimming segments, Abaqus is not able to understand that this is basically a geometric artifact, and was basically trying to mesh towards this direction, which then, of course, gives a mesh that is not usable. Then I have, let's say, almost a decade of experience handling immersed finite elements in different forms. So in a sense, this is an immersed finite element method. And I know this is going to be accurate. And this is also what we see. So if you compare accuracy of isogeometric trimmed shells versus Abaqus, it basically gives you the same result. Yeah? So this is displacements here. These are moments. Yeah, you see it's virtually the same. And if you focus in a little bit more on detailed accuracy along a trimming curve, you see you get actually exactly the same result. OK, now I want to switch gear a little bit, come to the second topic, and talk about physics-based modeling of lodging. So lodging is the phenomenon of plant materials to fall over under weather influence. Yeah, it could be storms or heavy rain, etc. And there are several mechanisms that underlie this lodging phenomenon. And one is creasing, which is basically the local buckling of the stem close to what we call a node. Yeah, the node is basically the location where the plants or additional stems grow out of the major stem. And so this is Professor Kevin Smith from the Department of Agriculture, and supported by the Minnesota Department of Agriculture. He is leading an initiative to found a new oat breeding program at the University of Minnesota. And the specialty about this oat breeding program is that it should focus on increasing the lodging resistance of oat crops. And a major task or a major challenge that this program faces right now is to identify quantitative trait loci in the oat genome such that they understand how to breed for an ideal variation of that variable. So this is where we come into play. So our goal is to identify these significant traits or these significant mechanical mechanisms that influence oat lodging via material modeling and simulation. So we're focusing on two aspects of the problem. One is we want to characterize the material by deriving a multiscale material model based on imaging data at the cross-section level. So right now we are focusing on the phenomena of creasing or local stem buckling. So we can assume that this material can be elastic. There's no material failure. But we need to really characterize this hierarchical level of material composition. And the second aspect we're focused on is on structural failure at the, let's say, stock scale level, where we also have imaging data to understand the composition of different regions across the cross-section and potential imperfections along the stock geometry. So what I want to illustrate or what I want to explain first is why hierarchical structure of plant materials is essential for this. And what we see here is a plot of the stiffness, so in terms of the Young's modulus, and on the y-axis in terms of yield strength for very different plant materials. And we see that we have a huge variety of strength, ranging from parenchyma-dominated plants such as apples and potatoes to very strong wood. Yeah, here's oak, and we see that that ranges from hundreds and megapascals to several gigapascals. Yeah, so there are orders of magnitude variation. And that is interesting in the sense that we know that all of these plants are composed by the same basic materials. And these are cellulose, hemicellulose, lignin, and pectin. So the difference in their mechanical properties comes from their hierarchical composition, their microstructure composition across several hierarchical scales. Yeah, so this is an example for bamboo that we focus on later, where we see we start at some polymer level. Yeah, we have cellulose that is connected to several fibril fibers, and then we are here. This is the cell wall level, which is an essential level, where we have basically base materials such as hemicellulose and lignin with embedded fibers in it. This level here is basically the functional mesoscale region level, where we connect these individual cells to different regions that serve different purposes. And then these functional regions are basically kind of assembled in a certain way to form the cross-section. And what we observe here is that these different scales satisfy something that we call scale separation. Yeah, so if we basically focus on characterizing a specific scale in terms of a representative volume element of length scale L, then we see that the components, the heterogeneous components of the lower hierarchical scale in terms of length scale D, are significantly smaller. And the behavior we're looking at, the stiffness behavior of the next level, yeah, that is composed of several of those cells, is significantly larger. And that's an essential property. And we're looking for microstructure stiffness relationships across different scales. And if we have proper scale separation, then we can use a technology called classical continuum micromechanics. That is a well-established field. So the idea here, or the task here, is to find microstructure stiffness relationships in terms of elasticity tensors that give us a relation between macroscale stress and macroscale strain, taking into account microstructural structural features. And I want to very briefly outline the basic components of this. So cornerstones of this theory are averaging theorems over certain so-called representative volume elements. Another component very important is the so-called strain concentration tensor that connects macroscale strain to microscale strain. And what we obtain basically are these microstructure stiffness relationships in terms of material properties of the microscale components and this strain concentration tensor. And if we assume that certain conditions are given, such as perfect bond between microstructures, microstructural components, and small deformation, and a certain geometry of your inclusions, then we can find explicit analytical expressions for these strain concentration tensors. Yeah, so this P here is intimately related to the relatively famous Eshelby solution. And so these analytical expressions give us tools to characterize different, or to connect different microstructural levels. So for example, we can focus on the so-called dilute composite case. Yeah, we have one inclusion in a relatively large matrix, but we also have other tools, for example, the Morita-Naka scheme, that basically can be used if you have several conclusions that are very close to each other and their interaction needs to be somehow taken into account. And we have also this self-consistent scheme, which is for morphologically disordered systems where you can't really understand what is an inclusion and what is in a matrix. So there's kind of an averaging procedure between different components involved. The important thing is to realize we can apply these homogenization schemes if we know, have we some idea about the geometry of this inclusion, because then we can find the strain concentration tensor. If we know the elasticity properties of the microstructure components, if we know volume ratios between the different components. So this is our, like an overview of our micromechanics-based material model. So we start at the cell wall level, where we basically model the cell walls that are basically in fibers included into base material. And we extract basically these components I just talked about from images. So this is a TEM image from which we know how many layers we have, how thick they are, and what the fiber orientation is. Then we go forward to these functional mesoscale regions. One, for example, is this parenchyma regions that is responsible for storage and for generating certain components that the plant needs. Another one is the vascular bundle region, which is responsible for transport of nutrients and water along the stem, and also for giving stiffness to the material. So here we can use the material from the previous homogenization step plus certain topological information that we get from scanning electron microscopy. And the final step is we can go then to the cross-section level and understand how big these regions are and how they are assembled to then finally find some let's say, material properties at the cross-section level. So again, the very important point here is if we know the stiffness of lignin and hemicellulose and cellulose, these are the base materials, if we have imaging information that gives us information about morphology of the microstructure at each hierarchical level, and if we know the volume fraction of the constituents, yeah, we can use, this model here is fully defined. So since we don't have enough information right now about the oat, so our target plant, yeah, we basically show the effectiveness of this model for bamboo, where enough information or extensive information exists in the literature. So here's just an example. So I'm focusing now what's happening on the parenchyma level, just to outline how one of those homogenization steps works. So what we have is we have these scanning electron microscopy pictures at the RVE level. Yeah, so these are single parenchyma cells. So we know their material properties from previous homogenization steps. So they're transversely isotropic elasticity tensors. Then from these pictures, we can understand the volume fraction of the cell wall versus these pore spaces here. We also understand the geometry of these pore spaces. And that is fully enough to come up with a scheme to understand how this material can be homogenized on the next hierarchical level. So the question now is, how accurate is this? And again, here we want to use bamboo because we have enough information. So here we use test results from a group at MIT led by Professor Gibson, who published extensive imaging data on the one hand and test results, mechanical test results on the other hand. So they basically tested different micro specimen across different locations of a cross-section. So here you can see that the parenchyma region, which is the brighter material, changes gradually towards the outer part where you have vascular bundles. And this gives us different specimens, basically, of different properties. They are characterized by different color points. And we see that for each region, yeah, we find a very, very good correlation between our model prediction and the experiment. Yeah? So this is an excellent correlation. So we know that our micromechanics-based material model yields or gives us very accurate results. And now, finally, I would like to illustrate how we are going to use this micromechanics-based model in stem buckling simulations. So here we ran a representative test case. Yes, this is basically one small section of a bamboo stem. And we applied pure moment by basically letting one side, letting it free to slide. So there's no chance to have any transfer any shear. And on the other hand, we basically apply a bending moment. And what I want to illustrate here is how important it is to have the correct orthotropic material tensor, because in a certain direction, yes, let's say in axial direction, it is possible to get these, let's say, stiffness parameters also from experiments in an empirical way. So here we test with empirical stiffness, and here we test with our micromechanics-based orthotropic stiffness tensor, or transversely isotropic stiffness tensor. And we see that buckling is largely influenced by this transverse isotropy. Yeah, so here you see the load displacement curve, and we see that the isotropic case is significantly stronger than the transversely isotropic case, where you have weaker material in the out-of-plane directions of the stock. The problem is now, of course, that these transversely isotropic properties are extremely hard to measure experimentally, because testing along the stock is possible, but testing in the transverse direction is hardly impossible. Yeah? But with this micromechanics-based model, we automatically can build up accurate material coefficients based on mechanics. Okay, I want to outline, this is work in progress, so our next steps, of course, is obtain enough information in terms of imaging data and material data from microimaging for our target plant, which is oats. And we also need to look a little bit into cross-section configuration in terms of imperfections, because these lines are dramatically influenced by how the, let's say, macroscale geometric configuration is set. And then we're also working on validation via macroscale experiments for the oats. So these are initial experiments that we ran. Okay, with this, I would like to come to the third and final part, and this is on the variational multiscale method. So the variational multiscale method is a general framework for deriving models and numerical methods for multiscale phenomena. And its main motivation for its derivation was to mitigate robustness issues of Galerkin's method in the presence of multiscale phenomena. Yeah, so Tom Hughes was instrumental, or was the main creator of this concept. And here is how it works. So we start from a weak form. So the weak form is basically a variational formulation of the physical problem that is characterized by some partial differential operator here. U is the solution, and W is a test function. And what you do in the next step is you apply so-called sum decomposition. So you split the solution as well as the test function into two different parts. A coarse-scale solution that is basically denoted here with this bar, and a fine-scale solution that is denoted here with this prime. And the same thing, of course, you do for the test function. So you can kind of think about you separate your function space into a coarse-scale function space that you would be able to kind of represent, for example, with a finite element discretization, and a fine-scale function space that represents everything else. So that would be associated with the error that you have. Due to the linearity of this test function split, yeah, you can split this variational form into two variational forms. So one variational form that depends on the coarse-scale test function. This is called the coarse-scale problem. And another variational form that depends on the fine-scale part of the test function. That here is the fine-scale problem. And then the idea is if you can come up somehow, yeah, so if you can use this fine-scale problem somehow to arrive at a solution for U prime, either analytically or numerically, then you can use this as a closure model in the coarse-scale solution to arrive at a fully closed form variational formulation that you can then use for finite element discretization, where the subgrid scale effect of things you're not resolving is fully included. And one way to do this in 1D, you can do this analytically, would be you could find U prime solution via Green's function, insert it here, and then basically come up with a finite element solution that includes the subgrid scale effects. This method has grown very popular in the finite element arena over the last 15 years, and it's now the state of the art, in particular when using the finite element method in so-called advection-dominated problems, for example, in computational fluid dynamics. So these are computations that were run by colleagues of mine, Ming-Cheng Xu and Yuri Basilevs. And the important thing here is to realize is, so they are using this method. So their mesh scale is basically at this level, so they can see, of course, the profile of your turbine blades. But in terms of the flow resolution, this mesh is not accurate or not fine enough to completely resolve all the physical scales of the problem in terms of eddies and vortices that are, of course, much, much smaller than that. So you can use this subgrid scale VMS idea to leverage this as an effective subgrid scale model. Yeah, where you have subgrid scales, you kind of come up with an approximation for these U primes that you can then insert into your coarse-scale variational form to have a finite element discretization that includes fine-scale effects. And at the same time, it turns out that this VMS method is a very good method, or is an effective method for stabilization of advection-dominated finite element schemes. The issue is that this solution procedure here, right now, its derivation is very strongly based on continuity of the basis functions so far. So why is that a restriction? That is a restriction for a new class of relatively new class of finite elements that is called discontinuous Galerkin methods. So in contrast to standard Galerkin or standard finite element methods where you have continuous basis functions, In the discontinuous Galerkin method, you have discontinuous basis functions because you start formulating your problem on one single element domain and then derive some element interface conditions in terms of integrations over these element interfaces that tie these elements together. Now the question is, why would you do something like that? And it turns out that there are significant advantages for this type of numerical scheme. For example, you have a rigorous mathematical foundation. You can apply this on unstructured general grids. You can have arbitrary order accuracy. This scheme here is stable, naturally stable for convective operators. It is locally conservative, which is a very, very strong argument for many, let's say, more application-oriented people in fluids who want to have local conservativity in a discretization scheme. It enables direct HP adaptivity. It is expensive because it, of course, has more degrees of freedom than the corresponding Z0 continuous basis. But it is very, very well suited for parallelization. Just to illustrate how strongly or how dominating this method has become in the CFD community. So this is a list of different groups that regularly meet at different conferences to test the capabilities of their CFD codes. And in this case, for example, this forced vortex example. And the interesting thing here is, so we see these are groups from both academia, from government labs, from Europe, and from the US. So this is not, let's say, a localized phenomenon, but we see that DG methods among the CFD community, especially among the higher order CFD community, has become become very dominant. So our idea is to derive a mathematically rigorous formulation of DG in terms of a variational multiscale format, which we anticipate can have significant effects in different areas. So one is it can have an improved DG-VMS capability for turbulence modeling. Yeah? Another one would be to enabling advanced cut cell FE technology because, as you probably remember from the slides that I showed during shell analysis, there's an intimate relation between immersed methods and the DG formulations. And there are probably many more, but these are the two ones we are interested in. So what I want to do first is I would like to review again the classical derivation of DG methods. So you start from a physical problem. So this is just a test problem here. And this is in mixed format, but it doesn't really matter. Then you derive, so this physical problem is basically defined on each element separately. So these elements are not connected. Then in the next step, you derive a weak form by basically integrating over that element domain and integrating by parts so that you get these flux terms that I already talked about earlier. And then you're introducing these numerical fluxes. So these are choices you take in order to introduce connections between different elements at element interfaces. And then you can arrive at this primal formulation of the variational format that contains the usual parts and these additional element interface parts that couple elements together. Okay, so what we have done is we have derived a way of deriving DG methods in a VMS framework, which turns out to be a completely new way of arriving at DG methods. So what we do is we start again from a partial differential equation. It's again an elliptic model. We assume here that our solution is C1 continuous. Yeah, this holds for most of the problems we're interested in particular for fluid in CFD that can easily be checked. I mean, the velocity is going to be C1 continuous. Then in the next step, we derive a per element weak form of each element individually. And what we can see is that we keep the weighted residual form. We don't do integration by parts yet. And then we associate this weak form with analytical or exact transmission conditions. Yeah, we say that the jumps of the solution and its gradient should be continuous across element interfaces. So here we define these DG-type operators. So this is a jump operator across an element interface, and this here is an average across an element interface. Then in the next step, we do something new. Yeah, we introduce our scale separation. So we separate the solution into a coarse part and and this Finescale part. And we do this of course, also for the test function. And then we arrive at our multiscale weak form that again has two parts. One coarse-scale part that depends on the coarse-scale basis function, and one weak, or one Finescale part that depends on the Finescale part of the test function. It also allows us to derive relations between the coarse-scale solution part and the Finescale solution part, and as well as the gradient of the coarse-scale solution and the Finescale solution at the element interfaces. This is not a numerical flux assumption, but it basically flows naturally from these transmission conditions and the scale separation. Then in the next step, we focus on the coarse-scale problem only. And then we do the following steps. So in the first step, we now do integration by parts, which gives us additional surface terms at the element interfaces in terms of the coarse-scale solution and in terms of the fine-scale solution. Then in the next step, we use these relations between coarse-scale and fine-scale parts at the element interfaces to derive expressions that we can plug into these surface terms. Yeah, again, these are not assumptions. These are still exact representations that basically take care of coupling these elements together. Yeah, so we have not introduced any approximation. This is still completely exact. And then we arrive at an exact global coarse-scale equation that contains the usual bilinear part. Here's the linear part. Then we have these additional surface terms that couple elements together. And we have a third class of terms that represent basically the fine-scale effects of the unresolved part of the solution. Yeah? So these things here all have U prime in it. So what I want to argue now is that you basically, if you look at this from a very, let's say, more high-level perspective, then I want to argue that this is a completely new generalized unifying framework for deriving discontinuous Galerkin methods. And this becomes very obvious if you compare this to the classical DG framework that was derived by Arnold, Bretzi, Coben, and Marini about 15 years ago that covers a certain number of methods. Yeah? So our framework is much broader than that. Yeah? It contains all of these cases here as special cases, and they can be re-derived by choosing certain closure models for our fine scale. But in addition to this, depending on how we choose these closure models, we can also arrive at completely new, not known discontinuous Galerkin methods by using this general framework. So what I want to do in the rest of the time that I have, I want to do two things. So first, I would like to outline how we can obtain from this, our general framework, how we can obtain specific known discontinuous Galerkin methods. And I choose the interior penalty method that was derived or introduced about 30 years ago by Doug Arnold in his thesis. So what we observe is that many of these terms already match. Yeah? So the regular bilinear form is the same. Yeah, we see that these interface conditions are the same. What is not the same is this specific interface term that Doug Arnold added here, that of course now somehow needs to correspond to our fine scale part. So what we do now is we basically, to obtain the IP method, we set our fine scale part equal to that extra term that Doug Arnold has. So when we say, okay, we are focusing for the moment on linear basis functions, this surface part, or this volume part vanishes, and only these surface parts stay, and that's of course directly now analogous to this. And now if we choose some specific fine scale, what we call fine scale interface models that are basically closure models, then we can arrive at an equality of this. And we can do that by setting, okay, the average of the fine scale solution across the interface should be the same, and the average of the gradient of the interface solution should be equal to that extra term that Doug Arnold found. It's clear it's the same, but in addition to this, a very, let's say, convincing argument for our framework is that it offers additional insight from a geometric point of view what happens actually at these interfaces. And this I want to illustrate with this problem here. That's a very small test problem in 1D. So this dashed line here, the dashed black line is the exact solution. Then we introduce a 1D finite element mesh in terms of DG elements. So these are the element nodes. So these are element interfaces. And they give us the red solution. So we can compute, as the difference between exact solution and red solution, we can compute these Finescale solution part here. That is normally not known, but in this specific case here, it's known. And if we then have focus on what's happening at the element interface, yeah, we see that we can get geometric interpretations of what is happening. So for example, the average of the Finescale solution, which can interpret as our error, is going to be 0. And the second thing is we can expand these terms in terms of a Taylor expansion, and then see that depending on this extra stabilization parameter that Arnold has, that we can transfer into a distance away from the interface in both directions, that depending on this extra term, we can see that this term makes the Finescale solution be equal in a certain distance of the interface. So we also now understand that, for example, if we introduce a very, very large eta here, which is the free parameter in Doug-Arnold's method, then these points will closer move to the interface, eventually making the Finescale solution equal at the interface. Yeah? So what I want to emphasize here again is that our model gives us much, much more intuitive engineering information about what this method is actually doing than the original formulation. Okay, the second thing I want to do is I want to talk about a little bit how these things can be made use of in an engineering context. And so our final goal is to use our formulation in something that is called a residual-based turbulence model. And how that works, I would like to illustrate with Viscous-Burgers equation, which is basically a 1D pressure-free Navier-Stokes equation. So it has this solution here. So we apply a DG method just based on four elements, and we find this dotted solution without our VMS-based model, and the red solution in terms of the VMS model with a subgrid scale model included. So a fundamental question, of course, is why is that Viscous-Burgers equation the right model problem for, let's say, 3D Navier-Stokes? And the fundamental argument for this is that the behavior, not in the spatial domain, but in the, let's say, in the energy spectrum, is equivalent to between Viscous-Burgers and 3D Navier-Stokes. So this here is the same solution, or the exact solution represented in terms of wave number and the corresponding spectral energy. And we see that it has the same form than for 3D Navier-Stokes, which is usually known as under the name energy cascade. So what we want to do is we would like to represent these energy or these spectral parts of the solution with our coarse-scale discretization, and all the rest of the solution parts that we can't represent by our coarse mesh should be taken into account by a VMS-based model. So we basically used, in 1D, you can easily derive a Green's function-based technology to exactly solve the Finescale part. So this is how we derive this part of the coarse-scale variational form that represents the behavior of the unresolved scales. And already from here we kind of understand that the red solution is better than the dotted blue one. But it becomes very obvious if we go to the energy, if you observe the energy, total energy of these solutions, so they are computed like this. And here we compute that of no model. That is basically, this here would be the error in the energy. Then we do this with a regular VMS model based on continuity at the interface. That would, in the DG case, do not give you any improvement in terms of accuracy. But our new model, that is basically a VMS model specially tailored for DG methods that has these also surface terms in terms of Finescale contributions, gives you a significant improvement in terms of the energy error across, for a 1D problem, a wide range of degrees of freedom. So of different meshes, we can see consistently that the energy error is significantly lower than in the standard approach. So this is basically the result that gives us, that motivates us to further look into full 3D problems in terms of the Navier-Stokes equation, apply this, and find similar solutions. Okay, now I would like to come to an end and sum up what I talked about. So I first talked about isogeometric shell technology of trimmed CAD surfaces. So I talked about the poor interoperability between today's CAD and FEA tools. I talked about isogeometric analysis that constitutes an opportunity for fundamental change. And I talked about our approaches to arrive at an accurate and robust technology to handle trimmed shells in the context of isogeometric analysis. In the second part, I talked about micromechanics-based modeling of plant materials. So the main goal here was to derive accurate structure stiffness relationships between different hierarchical scales of a plant material. And I tried to outline how that can be critically supported by imaging technologies. And a major point here is that we can, with this micromechanics-based model, we can model mechanisms in terms of transverse behavior that are impossible or very, very hard to obtain experimentally. And in the third part, I talked about discontinuous Galerkin methods in a variational multiscale format. So I showed an alternative derivation and what we think is a completely new interpretation of discontinuous Galerkin methods. I tried to stress why we believe that this is a significant potential for designing effective subgrid scale models, for example, as a turbulence model in CFD simulations. And I think that this, in the future, that this has potential for being used as advanced cut cell FE technology and to hopefully motivate new DG schemes based on new closure models. And with this, I would like to close. Thank you for your attention. And of course, credit my fantastic group of students, in particular, Taron, who works on the plant project, and Stein, who's the inventor of the DG work. And then I also have very, very good collaborators. So this is Yuji Guo, who is an assistant professor at the Nanjing University of Aerospace and Aeronautics. So he did many of the shell computations were done by him. Then these are folks from biomechanics and agriculture who are with me together, or with us together on this plant project. And then I collaborate with Steve Holzoff from TU Delft and Bernardo Coburn on the DG work. So Holzoff is an expert in turbulence modeling, and Bernardo is a world expert in terms of the development of DG methods. And I also would like to thank my funding agencies, in particular NSF and the Minnesota Department of Agriculture. Thank you.
Thank you very much for a very excellent lecture. Are there any questions for Dominik? Okay, I'll take the microphone to you.
A common topic in some of aspects of your presentation was DG method.
Yes.
And from what I know about this method, they require special parameters to define that properly. And the results can be quite sensitive to the selection of those parameters. So I wonder how you choose those, if that's necessary.
So let me go. I think this slide would be appropriate. So you're talking about parameters that somehow are in the classical framework. So we see a parameter here, the beta, for example, then the eta here would be a parameter. This one doesn't. Here we have parameters, and here. And the major point I want to make is that this one is at a much higher level. We haven't introduced any parameters. So these parameters would come by choosing closure models for the Finescale effect. And depending on how you do this, you have to, of course, also introduce parameters, for example, to stabilize. But we are at let's say, one level up, where we haven't made any choices. Yeah, so all these methods are included here, depending on how you choose your closure model. And that would also then give you the same parameters that you have. Of course, these parameters would also then be there and would have to be resolved in the same way. The second thing is, if we go to this level, sorry?
So the choice of the closure model includes implicitly some parameters?
Absolutely, yes. So for this one here, for example, we didn't have any parameters. We could exactly solve it in terms of Green's function. If you can do that, that won't be possible in the 3D case. So we also have to start then thinking about introducing certain approximations that come along with, I would presume, certain parameters that we have to choose.
How about the shells?
Yeah, the shells, of course. In the shells, we use the IP method, and that has parameters. So let's look at this one. So here the idea is, so there exists a method to automatically choose these stabilization parameters. These stabilization parameters you're talking about are these alphas here. So they need to be, so if you're using your weak form without these stabilization parameters, you could lose, in the worst case, you could lose coercivity being stable. So they need to be large enough. So you can use that coercivity relation to, including these terms here, to include, to derive, consistently derive conditions on these alpha terms. And with some numerical analysis tricks, you can transfer the problem of choosing alpha explicitly in terms of an eigenvalue problem that involves cut elements. And so you can choose them from a local eigenvalue problem. You can come up with a minimum stabilization parameter that will make your method work. Let's put it this way.
So when you discuss the multiscale analysis, right, you assume additive decomposition of the scales, but that does not necessarily hold. You have examples when you have a multiplicative one, for example, let's say a block wave function. So in general, in the math literature, when you do the multiscale analysis, you just keep it as a function of two variables. Then you go through your chain rules and obtain whatever you get. So what are the limitations of the assumption of the additive decomposition of the scale variations in terms of your formulation?
I mean, yeah. So this is probably best summarized here. So you're referring to the split?
Correct.
So in principle, this split does not mean. I mean, I'm thinking about how you could do a multiplicative split of this, because this split is meant in terms of this. So you have your exact solution, which is in terms of a function space that contains all components that you have, and then you basically pick some components that you can represent in terms of your Finite basis functions, and all the rest of them are not represented, so you basically lump them into a space that in this space. And so all formulations I know are perfectly fine with this split. So I wouldn't know how you would do a split in terms of a multiplicative split.
So this is just one example, but let's say here the
because
consequence.
Even if you had multiplicative splits, for example, in a plasticity model, you could still add this in there. It would work out. I mean, you do the split in terms of the space. So I'm not. I mean,
well, the consequence would be that this
into two parts. How do you want to do? How would you motivate a multiplicative split between them?
Okay, we can discuss this after the lecture.
Thanks.
In your micromechanically motivated modeling, you really look at, if I understand well, at material linearity and the problem that you are looking at geometrically nonlinear, because you are looking at creasing and buckling, but all the homogenization technique is based on elasticity. So I'm just wondering if you had to consider yielding. At what scale would you operate, and how would you do it? I mean,
that is a very interesting question. So, so right now we assume that all that transfer is linear up to this point. So in the finite element model at the macro scale, we then allow large deformations. That's why we get this buckling phenomenon. So if you go from, let's say, no material failure to a model that also includes material failure in terms of yielding effects, for example, then these yielding effects are known not to be up here, but to be at the cell wall level. So that then, of course, introduces the problem that you also have to upscale strength. And our idea right now is to do something. So usually that means if you want to do that in, let's say, as realistic as possible way, you would have to go away from analytical approaches to let's say, computational approaches. Yes, we would do computational homogenization. But since our model, our analytical model, works so nicely, we would like to keep that one and also try to upscale strength parameters. So what we want to upscale is plastic strain. And for that, our idea is to decompose that from elastic strains and treat it as a separate variable. And then try to basically, at some point, basically also include plastic strains at a certain level. And then upscale that in the same way with the same type of technology we have, analytical technology, as we have it for the elastic part. So that would be our first idea to do that. And we're working on that right now.
We'll do one more question, and then I think we need to finish.
Hi, Dominik, I was wondering about the plants, if they're, say, fully hydrated, filled with water versus dry, how would that impact your simulations?
It will affect it. Right now, the situation is that we have tests for undrained. So we'll let water out of the question. And that is also our own experiments. So when these samples arrive from St. Paul here on campus, then they're basically, the proper way to treat them would be in an undrained state. If you want to have things like turgor pressure included, then you would have to go back to your to this level here, and there exists theories to add that to that, yeah, in terms of so this here is already called micromechanics, and so there's a complete let's say let's say drained condition part of that theory included, and we could directly use that one.
Okay, well, I would like to have you join me in thanking Dominik for a wonderful presentation.